everyone. I hope you're doing well. Today we're going to wrap up our discussion on buffers, and next time we're going to look at titrations of acids and bases. And today we're going to start by discussing basic buffers. Previously, we showed different types of acidic buffers, which consist of a weak acid and its conjugate base. But buffers can also be composed of a weak base and its conjugate acid. And the conjugate acid is usually in the form of a salt. So for instance, down below we have the example of ammonia and its conjugate acid, the ammonium ion. But typically, the ammonium ion is ionically bonded to, for instance, chloride, just to balance the charge. So in this case, we have ammonia again, and its conjugate acid. And if we add approximately equal amounts or exactly equal amounts of both into solution, we'll end up with a buffer. So let's talk about buffer effectiveness. An effective buffer neutralizes moderate amounts of added acid or base. However, there is a limit to how much can be added before the pH changes significantly. So if we add way too much acid or way too much base, we're going to overwhelm the buffer. And again, we only have so much weak acid and its conjugate base, or weak base and its conjugate acid. So eventually we're going to run out of weak acid or weak base, and we can no longer neutralize any added acid or base. So the buffer capacity is the amount of acid or base a buffer can neutralize. And then the buffer range is the pH range in which the buffer can be effective. So we'll talk about those two in a little more detail. And the effectiveness of a buffer depends on two factors. One, the relative amounts of buffer acid and base. And two, the absolute concentrations of buffer acid and base. So we'll talk about that as well. All right, so buffer capacity, again, is the amount of acid or base that can be added to a buffer without causing a large change in pH. And buffer capacity is going to increase with increasing absolute concentration of the buffer components. So as the buffer concentration increases, the buffer capacity also increases. And this makes sense, right? The more buffer base we have, the more acid we can neutralize. The more buffer acid we have, the more base we can neutralize. So we typically want our buffers to have a pretty high concentration of both acid and base. And here's a visual where we're showing a concentrated buffer on the left and a dilute buffer on the right. So you can see that in the left-hand beaker, we have a more concentrated buffer. So that means that we have more weak acid and its conjugate base, which can neutralize any added acid or base pretty well. And we're not going to run out of weak acid or base very quickly. But in the dilute buffer, we only have so many weak acid molecules and weak base molecules, so we're going to run out of those pretty quickly, and then we'll no longer be able to neutralize any added acid or base. So again, a concentrated buffer can neutralize more added acid or base than a dilute buffer. So let's talk about the ratio between the weak acid and its conjugate base. So as the concentration of buffer base to buffer acid ratio approaches 1, the ability of the buffer to neutralize both added acid and base improves. So we want the concentration of base in the buffer to equal the concentration of acid. Or if they're not exactly equal, we want them to be pretty close to each other. Now, sometimes we do need a ratio that's slightly off of 1. So for instance, if we're using a buffer that needs to work mainly with added acid, we want the concentration of the base in the buffer to be slightly greater than the concentration of the acid. So if we have more base than acid, the buffer can neutralize added acid. Added acid. So that makes sense, right? The more base you have, the more acid you can neutralize. And then also, if we were working with a buffer where we knew that we were going to add a lot of base, then we want the concentration of the acid in the buffer to be greater than the concentration of the base in the buffer. So sometimes we want the concentrations of our buffer acid and base to be a little bit different depending on what type of experiment we're running. But most often we want the concentration of the buffer base to equal the concentration of the buffer acid. All right, so we said that a buffer will be most effective when the ratio of acid to base is 1. So we want equal concentrations of acid and base, ideally. Now, if we do need to change the ratio slightly because we know that we're adding more acid or we're adding more base, then we do have a range in which a buffer will be most effective. So the ratio of base to acid should be between 0.1 and 10. And we'll go over that in a little bit more detail next. And then a buffer will be most effective when the acid concentration and the base concentration are large. So the more acid and base we have, the more added acid or added base we can neutralize. So let's talk about buffer range a little bit more. So we said that a buffer will be effective when the ratio of base to acid is between 0.1 and 10. And remember that that ratio of base to acid is what's in the Henderson-Hasselbalch equation. So we want that ratio or that fraction to be between 0.1 and 10. And then that tells us that a buffer is effective. So if we're trying to choose a buffer to use, down below we can see, what type of range we're looking at. So the lowest pH that we want, or that a buffer can effectively neutralize any added acid or base, is equal to the pKa minus 1. So all we did there was we plugged in 0.1 into the ratio of base to acid. And if we plug in 10, which is the higher end of our range, we can see that the highest pH at which a buffer will be effective is equal to the pKa plus 1. So what this tells us is that the effective pH range of a buffer is pKa plus or minus 1. So when we're choosing an acid to make a buffer, we want to choose one whose pKa is closest to the pH of the buffer. So, for example, we previously saw that the pKa of acetic acid buffer is 4.7. So, let's say we're trying to maintain a pH of 5. Then we would want to pick acetic acid as our buffer because it's going to maintain a pH of anywhere from 3.7 up to 5.7. So that's 4.7 minus 1, and then 4.7 plus 1. So let's actually go over an example. And we're going to compare the effectiveness of two buffers upon addition of 0.01 moles of hydroxide ions, or strong base. So in solution 1, we have equal amounts of acid and base. So we have 0.1 moles of acid and 0.1 moles of base. And then the initial pH of this buffer is 5, and the pKa of the acid is also 5. And then in solution 2, we don't have equal amounts of acid or base. In fact, we can see the concentration or the amount of acid is much greater than the amount of conjugate base. So we have 0.18 moles of acid and only 0.02 moles of conjugate base. So the initial pH of this solution would be lower because we have so much acid. So the initial pH is 4.05, and then we're assuming that we're using the same acid, so the pKa is equal to 5. Okay, so let's start with solution 1. And we're going to write out the equation for acid and the base that's added. So again, the base is going to grab onto the hydrogen on the acid, so we'll end up with H2O as one of our products. And then what's left over is the conjugate base. So before addition of any strong base, we said that we have equal amounts of acid and base. And then we're going to add 0.01 moles of strong base. And once we add the base, it's going to completely react with acid. So we can determine the new concentration of acid by subtracting the amount of base. And everything here is reacting in a 1-to-1 ratio, so we don't really have to take stoichiometry into account. But after the reaction is over, we'll have 0.09 moles of acid left. And then in terms of base, we're going to have an additional 0.01 moles. So we have 0.110 moles of conjugate base. And again, we're not going to have any of our strong base left over. We're assuming that it's completely reacted. So now we can plug in these amounts into the Henderson-Hasselbalch equation. Okay, so we were told that the pKa is 5, and then we're going to plug in those calculated amounts of base and acid. So our ratio there is approximately 1. It's a little bit greater than 1. So we're going to end up with a pH of 5.09. So this buffer did a pretty good job of maintaining the pH. It didn't change by very much, but let's calculate the percent change, just so we have that value handy when we're comparing the two buffers later. So to calculate the percent change, we're going to take the difference in final and, oh, that should be a 9. So we're going to take the difference in final pH and initial pH, and then we'll divide that by the initial pH and multiply by 100 to get our percent. So we'll end up with a percent change of 1.8%. So that's pretty good. Now let's compare that to the other buffer, which had way more acid than base. So let's write out that same chemical equation again. So the weak acid is going to react with the strong base to produce water and the conjugate base. And then before the addition of any strong base, we had 0.18 moles of acid and 0.02 moles of conjugate base. And then we're adding 0.01 moles of strong base. And then after the addition, we know that the weak acid and strong base are going to completely react with each other. So we can subtract the amount of strong base from the initial amount of acid, and what's left over is 0.17 moles of acid, and we're not going to have any hydroxide ions left over because they all reacted. And then we should end up with more conjugate base, so we're going to add 0.02 and 0.01. So after this reaction, we'll end up with 0.03 moles of conjugate base. Okay, so now let's plug these values into the Henderson-Hasselbalch equation. Okay, so the pKa is still 5. We're using the same acid here. And if we look at the ratio of base to acid, it's really small. We have 0.03 over 0.17. And if we calculate the new pH, we get 4.25. So the pH has changed significantly in this case. And let's calculate the percent change so we can compare it to our previous solution. So again, we're going to take the difference in final pH, which was 4.25, and initial pH, which was 4.05. And then we'll divide that by the initial pH and multiply that by 100. And this will give us a percent change of 4.9. So what this tells us is that we do want a buffer that contains approximately equal amounts of acid and base, or exactly equal amounts of acid or base. If we have too much of one or the other, it's not going to be a very effective buffer. And in this case especially, where we had significantly more acid, it was able to react with the added base, but we didn't have enough of the conjugate base to give us a better effective buffer. So really the conclusion here is when the concentration of the base is equal to the concentration of the acid in our buffer, the buffer is more effective. And then additionally, remember that we want pretty high concentrations of both acid and base. All right, so next time we're going to talk about titrations. You've already gone over lab 1, so you were able to see what a titration curve looks like, and you analyzed the titration curve. And now we're going to dive in a little bit deeper and talk about how we can calculate the change in pH as we add base to acid. So I will see you in the next video.